So in the last video, we went through a lot of different definitions in the context of nonlinear difference equations. So things like stability, whether or not a solution is attracting, what an equilibrium solution is, and all that jazz. So in this lecture, we're going to go back through and actually make some of these definitions a little bit more concrete by giving specific examples in each of these cases, and also pointing out some of the various edge cases that can arise. So let's get started. Let's start by giving an example of fixed points in equilibrium solutions. So let's do that down here. And let's start with an example. So we're going to let f of let x sub t plus 1 be equal to x sub t over 2 plus 5. Well, then it's pretty easy to check that x bar equal to 10 is a steady state solution, or equilibrium solution. So I'll be using those terms interchangeably in this lecture. Why is that? Well, if you plug 10 in, well, 10 divided by 2, for x sub t, 10 divided by 2 is 5, plus 5 is 10, and so x sub t plus 1 is also 10 if x sub t is 10. And of course, then 10 is a fixed point of the function, so in this case, here, this is equal to f of x sub t, where that is x sub t over 2 plus 5. So it's a fixed point of the lat function f. Let's give another example. Let me do this as an example for a fixed point of a system of first order equations. So we're going to let x of t plus 1 be equal to, let's say we had some matrix. 1, 2, 0, 1, x of t. So this is a two-dimensional vector. Well, then x bar equal to 1, 0, so this particular vector is a steady state solution, or an equilibrium solution. And that's because if you multiply the matrix in, if you see that if you start with some x naught is equal to 1, 0, you multiply by the matrix 1, 2, 0, 1, you still get 1, 0, and so that is a fixed point of the function defined by your matrix, and also an equilibrium solution of your linear system of linear difference equations. Okay, so that was an easy one. So a fixed point is just something that stays the same. An equilibrium solution is just something that stays the same. The next thing we talked about were these periodic solutions, these solutions that start at some point and then go around in some big long path and then come back to the starting point. If it takes m steps to go around the entire path and come back to the starting point, well then we call that a periodic solution of period m. And we can do the same, and then the path that it takes is called an m cycle, and we sometimes also call it the periodic orbit of the starting point, because that's the path it takes, the orbit it takes before it comes back around to its starting point, sort of like the Earth going around the sun. And let's give a couple of examples of these. So let's actually compute some of these. Let's see, give myself some space here. And let's start with an easy example. Let's suppose that we're going to let x sub t plus 1 be equal to f of x sub t, where f of x is equal to minus x. So you should be able to see where this is going. Well, then x bar in the real numbers for any x bar not equal to 0 is a periodic solution of period 2. Right? If you start with 5, well, after you apply the function f once, you get minus 5, you apply it again, you get 5 back. And so it takes 2 steps to get back to its starting point, and so this is a solution of period 2. And, well, let's suppose that x bar is equal to 0. Well, we know for lat then f of 0 is equal to 0, so this is a steady state solution. Steady state equilibrium instead. We're not going to call it a periodic solution, even though you could, in theory, call it a periodic solution of period 1, because it's just easier to talk about it remaining constant, and so using the term steady state. So that was a bit of a trivial example. Let's do one that's a little bit harder. So suppose we have x sub t plus 1 is equal to ax sub t over b plus x sub t, where a and b, and that'll be a function f of x of t by definition, and where a and b are greater than 0. Now in this case, we can't just stare at it and see the equilibrium solution like we did for some of the other ones, so we actually have to solve for it. So to solve for an equilibrium solution, we want to solve the equation x bar is equal to ax bar over b plus x bar. Well, in order to solve that, we multiply both sides by b plus x bar. You get x bar times b plus x bar is equal to ax bar. So then x bar squared plus bx bar minus ax bar is equal to 0. Factor out the x bar times x bar plus b minus a is equal to 0, which implies that x bar is either equal to 0 or a minus b. And these are our two equilibrium solutions. Let's have some more space. So these are the equilibrium or steady state solutions. And if you plug each of these back into the original difference equation, you'll find that you get the same thing back again. So there are two of these in this case. Now, let's ask another question. Are there any 2 cycles? So periodic solutions with period 2. Well, in this case, to find 2 cycles, we need to solve for something similar. Solve for f squared of x bar is equal to f of x bar, and we want that to be equal to x bar. So we want it after you apply your function f twice to return to the original solution. And this is a little bit more algebra to compute, but let's do it anyway. So this implies that if you plug it in f of x bar, we knew to be ax bar over b plus x bar. And we want that to be equal to x bar. You plug in that entire value into x bar in your function f again, and that ends up giving you that a times ax bar over b plus x bar over b plus ax bar over b plus x bar is equal to x bar. And that, let me go ahead and just write it here to start save a little bit of space. So if we multiply both sides by this term here, you get that a times ax bar over b plus x bar is equal to bx bar plus x bar times ax bar over b plus x bar. And if we keep on going, that ends up multiply both sides by b plus x bar. So you end up getting a squared x bar is equal to b squared x bar plus b x bar squared plus a x bar squared. Do a little bit more algebra, you end up getting that a squared minus b squared times x bar minus a plus b times x bar squared is equal to 0. And you note that you can factor a term of a plus b times x bar out of both of these, and you're left with a minus b minus x bar. So that product is equal to 0. And of course, this implies that x bar is equal to 0, or x bar is equal to a minus b. But you'll note that those are the same as our equilibrium solutions up here. And so, let me write this down. But both of these actually have period 1, because they're equilibrium solutions. Period 1, because they are equilibria that we found earlier. Equilibria that we found earlier. So there are no 2 cycles. In this particular example, we don't actually have any periodic solutions of period greater than 1. And of course, the period 1 solutions are just the steady state solutions. Okay, so that's what we mean by periodic solution. It's something that goes around and eventually returns to the starting point. And now there are several different kinds of behavior in equilibrium. So let's go back to equilibrium solutions now. And there are several different kinds of behavior you can have for these equilibrium solutions. So these things that after you repeatedly apply your function stay the same. So one criteria is this criteria of local stability. What it means if something is locally stable is that if you start close to your solution, you don't get too far away from it. So you might get a little bit farther away, but you don't get too far away. And if that's not the case, then you call it unstable. So let's give a couple of examples of things that are unstable versus stable. And I'm just going to use pretty simple ones here. So let's see, one easy example is x sub t plus 1 is equal to 1/2 x sub t. Now this has a locally stable solution, stable equilibrium solution of x bar is equal to 0. Why is that? Because when you start close to 0, you don't ever get farther away. In fact, you're always getting closer. You don't have to always get closer. You can go away for slightly further, but you have to come back. You can't get too far away for it to be stable. And moreover, this has to be true for any epsilon. There needs to exist some delta such that if you start close enough, you don't get too far away. And let's give another example. So this one is going to be the opposite of this. So x sub t plus 1 is equal to 2x sub t. So this has a locally unstable equilibrium. Locally unstable equilibrium solution. And it's the same solution, x bar equal to 0, because you plug in 0 and multiply by 2, you still get 0. However, the difference is that this time, if you start away from 0, you keep on going further away. So this is a very trivial example of an unstable solution. There are going to be some other more complicated unstable solutions we see later, but this is one of the simplest possible ones. So now, a closely related but not identical concept is whether or not something is locally attracting. So here we just said that if something, for stable, all it means is that something that starts close can't get too far away. For attracting, we actually want it to end up at our final point. So that's what we mean here when we say that there exists some gamma greater than 0. So when we say we need that because this is locally attracting and not globally attracting. So if you start within the ball of size gamma around your point, then you have to end up, as time goes to infinity, actually limiting to the equilibrium solution. So that's what we have here. And let's see an easy example of this. So, well, we already saw one of these examples, right? So x sub t plus 1 is equal to 1/2 x sub t has a locally attracting solution. Being solution x bar is equal to 0. And of course, in our other example, that was not the case. Equal to x sub t. In this particular case, even though x bar equal to 0 is an equilibrium, it is not a locally attracting solution. It is not a locally attracting solution. And furthermore, we can, so we've already seen one of these examples. So if something is both locally attracting and stable, well, then we call it locally asymptotically stable. And as I said, we've already seen one example of that. X sub t plus 1 is equal to 1/2 x sub t has a locally attracting stable solution. Locally stable attracting solution. X bar is equal to 0. Now, as I said, a very important note is that it's possible to be locally attracting but not stable. Now, if I were teaching this class in person, I would take this moment and I would ask you guys if you can come up with any examples. Instead, though, I'm going to give you one of the examples from the book. And so for an example of this, we'll see that, let's suppose we start with f of x is equal to a, this is a single equation, x plus 1 if x is less than 1, and 1 if x is greater than or equal to 1. Note that this function f is discontinuous. And you are allowed to have this in difference equations, although it does make life rather more complicated. So one way of thinking about this is if we start on the number line, let's say 0 is here, 1 is here, etc. Minus 1, etc. So if you start at some point here, well, then the next step you're going to take is going to go here, and the next step is going to go, let me see if I can draw this well. The next step is going to go here, and the next step is going to go past 1. But then the final step, because it's greater than 1, is going to go there. And so this is locally attracting because it has an equilibrium layer. So, it's locally attracting because 1 is an equilibrium, and no matter where you start, you're going to get there. If you start all the way on the positive side of the real line, you're just going to go straight to 1. Start on the negative side, you're going to slowly take steps by steps, slowly take many steps until you reach 1, until you reach just past 1 and then go back to 1. So let me write that out. X sub t plus 1 is equal to f of x sub t has an equilibrium solution at x bar is equal to 1. Just plug in 1. Obviously, if you plug in 1, it's just going to still be equal to 1. And it's locally attracting. It is locally attracting. In fact, it's actually globally attracting, but we haven't defined that yet. But it's locally attracting because the limit as t goes to infinity of x sub t is equal to 1 for all initial conditions. But now, let's see that it's not actually locally stable. So we're going to let epsilon be equal to 1/2. You can choose other epsilons, but this is a nice round number. So epsilon is equal to 1/2. Then for the range x naught that's greater than 1/2 and less than 1, we know that x1 is greater than 3/2. So x1 minus 1 is greater than 1/2. So there is no delta greater than 0 that works. So it doesn't matter if you start really, really close to 1 on the left side of, just smaller than 1, because what's going to happen is you're going to jump. And so for these values of epsilon, because you jump all the way over to the side before you come back to 1, these are not actually locally attracting because they get far away before they come back. And let's also give another slight example for locally stable but not locally attracting. So for this, I'm going to give a slightly more complicated example, but it's going to be a system of two first-order difference equations, x sub t plus 1, and I'm going to write it in matrix form. X sub t plus 1 is equal to cosine of theta minus sine of theta, and cosine of theta times x sub t, which is of course a two-dimensional vector. Now, you should hopefully recognize this as a rotation matrix. So this is a rotation matrix where theta is the angle of rotation. So that's the amount you rotate by in each step. Well, then we know that x bar is equal to the origin, 0, 0, is a locally stable equilibrium. Because if a point starts out in distance x of 0. So I'm going to use Euclidean distance here. If it starts out less than r, well, len the distance x of 0 minus x bar is going to be less than r forever, because it's just rotating. So it doesn't actually, oh, sorry, it's less than r forever, because it never actually changes. So the distance from the origin remains constant under this rotation function. And so it is actually locally stable, because for any, what was their definition of locally stable again? It was that, let me go back up to it. It was that for any epsilon greater than 0, there exists some delta greater than 0, such that if it starts close enough, if it starts closer than delta, then it remains closer than epsilon the entire time. In this case, you can just set delta equal to epsilon. So if you start within r distance, it's going to stay within r distance forever. And you can do this for any r. So it's a locally stable equilibrium, but you'll notice that the limit also never goes to 0. So for any x of 0 not equal to 0, 0, it will never converge to 0, 0, since the matrix is just rotating. So if we draw this out, if we, let me go ahead and draw a circle of any radius, but if you start at some point, say this is x of 0, well, len, you're just going to rotate up to x of 1, and then rotate up to x of 2, and so on. It's going to keep on rotating around, and no matter where you start from. In fact, this is, if your ANGO is rational, this will end up giving you periodic solutions because you rotate back around to your starting point. If your ANGO is not rational, well, then you'll just keep on rotating around forever, and it's not actually periodic with a finite period. But anyway, let's going beyond what we're talking about for this example. The conclusion here is that it is not locally attracting. Okay, and I'm just going to finish off with a little bit more intuition about what these different terms mean. So I'm going to try drawing it out a little bit. So let's suppose that this is our solution, and let's say that we have, let's put a circle of radius delta around here, and a bigger circle of radius epsilon around here. And so stable means that if a vector starts within distance delta, it stays within distance epsilon forever. So if you start, let's say you start at a point here, well, maybe you go there, maybe you come back here, maybe you go back out, maybe you circle around for a bit, maybe you come back, maybe you don't come back. But you can keep on going, and whatever happens, you stay within this ball epsilon, assuming you start out with some delta. And so what stable means is that for any epsilon, you can find some small enough ball delta that you never go farther than epsilon. Now, on the other hand, attracting means that, locally attracting means that if we start out with some ball around here, so this is ball distance gamma, attracting means that in the limit, if a trajectory, let's call it a trajectory, starts within distance, oh sorry, I meant to put gamma there, not delta, gamma, within distance gamma, then it converges to the equilibrium. So if you start somewhere around here, well, eventually, and you don't have to necessarily go in the same distance all the time, but eventually it has to go to our steady state solution there. Okay, so that ends this particular lecture. I just went through some examples about what stable means, what attracting means, and the just general definitions of periodic and fixed solutions and steady state solutions of first order difference equations and first order systems. In the next lecture, we'll talk a little bit more about local stability, but for that, I'll see you next time.